Tim?
Yes, thank you, David. We're going to go over today the best ways to install millimeter wave. Millimeter wave is fundamentally different than normal lower band RF, and we're going to go over some of those differences. This is going to be rather product light. This is more technical into what is millimeter wave, and what you're going to learn here today should be applicable not just to our equipment, but any millimeter wave equipment. And that's kind of what we want to focus on here. Just a little quick on who is SFU. We're a company that's been around now for about 10 years. We're one of the few manufacturers in millimeter wave that does both multi-point and 60 gigahertz, and we do point-to-points. We do the full suite of devices. We now are deployed in over 40 countries. We've got right now over 70,000 links currently deployed. Last year, we represented in the US 86% of all registered FCC links. Once you got rid of what's called duplicate registrations, we represented 86% of all registrations that the FCC had last year. So here's what we're going to cover. First off, we're going to talk about what is millimeter wave. We're going to go over some use cases, and then we're going to do a Q&A. So first off, why millimeter wave? It is simply, it's not that other people are building bad devices. There are a lot of good manufacturers out there. The issue is the bands. Sub-6 is getting incredibly congested. And, you know, and whether and it's not just LA or Chicago or New York or Miami, it's Peoria, Illinois. It's Salt Lake City, Utah, or even smaller towns. You're seeing the RF noise floor just get nearly unusable, and it's only going to get worse because you're only going to see more and more devices, especially since many of the cable providers on their client devices are now not just doing 2.4 on their client devices. They're actually doing 2.4 and 5.8. In fact, you can see it market by market when they introduce their new client devices. It actually causes the 5.8 north floor to even go higher. So what is millimeter wave? It's 5G, and that's really what 5G is based on, is millimeter wave. Specifically what Verizon uses is they own the 28 and 39 gigahertz bands. That's their own license bands, but it's a relatively small chunk of spectrum. Give you an idea of it right here. So right here is sub-6, and you can look down below and see the lower bands right there. And then as you work on up, and you can see right there where Verizon's bands are in 28 and the 38 gigahertz spectrum, it's really not that big a chunk. If you look up here at millimeter wave, you essentially have the V band, which is 60 gigahertz, and the new band is what the FCC approved about 6 months ago. It essentially doubled the amount of space that's available in V band. It's a tremendous amount of non-overlapping channels. I mean, considering that a typical non-overlapping channel in a 2.4 or 5.8 is 20 megahertz, our standard channel size is 500 megahertz. Okay, on E band, we've got 8 non-overlapping 500 megahertz channels. In V band, we've got over 26 500 megahertz non-overlapping channels. It's a massive amount of spectrum. Okay, so it's wide channels and high capacity, just like I was talking about. And you essentially have the E band, which is lightly licensed, and V band, which is unlicensed. And the other really cool thing is that it is this amazing abundant spectrum with these really small Fresnel zones. In fact, because the beam is only 7 millimeter, it's very, very small. So kind of doing a comparison between the two bands, V band is essentially, it's license free, and you've got the two sectors. And the neat thing about the new section of the V band is it moves out of the oxygen absorption zone. The existing band was, and part of the reason why it was unlicensed originally is because it could only go about 750 meters or about 2,200 feet, because it got limited because 60 gigahertz would excite the oxygen molecules. The new band, especially as you get farther up in the spectrum, it operates outside of the oxygen absorption zone. It's a very steep curve, and therefore performance now is rather than 750 meters, it can go out to a full kilometer and even beyond just with a small 6-foot antenna. E-band is lightly licensed. It's $75 for 10 years. That is the standard licensing cost from the FCC, and that's if you do your own self-filing. If you have somebody else file for you, it's going to be somewhere in the neighborhood, roughly about $350. That's for 10 years. And also, it's very quick. The process can be done in a matter of hours rather than days or weeks with lower band microwave. And it is absolutely, though, a line of sight. And the only thing that really affects it is rain. And to kind of go over the factors that count is this. It's really rain fade. And rain fade is because the bottom line with millimeter wave is millimeter wave, whether you're at 100 feet or 1,000 feet or miles, the throughput stays the same. What changes is the availability. Now, when we start talking about millimeter wave, is that essentially that in rough terms, a 1-foot dish goes about a mile, a 2-foot dish goes about 2 miles. That's sort of a rough approximation, but we do have links, and we'll talk about that here in a bit, that will actually go, and we have links going all the way out to 10 miles, and we'll talk about that in a bit. Things that don't affect millimeter wave is interference. You just simply don't have interference with millimeter wave, especially in point-to-point links. You don't have flat fade, depolarization, co-channel interference, fog, dust, snow, doesn't affect millimeter wave. And I'm going to put a little caveat on snow. If it's the big gloppy rain, heavy water content snow, that might affect it. Because really what will affect it is raindrops over 7 millimeters. In other words, raindrops bigger than the waveform itself, okay? To kind of dive a little bit deeper in it is that availability is the key. As you can see here, as we go in distance at 99%, we're still going to deliver full throughput. This is our 10 gig radio, okay? But as we go in farther distance, you can notice that your availability is dropping. So it's availability or the amount of uptime. So when we start talking about availability, we're looking at the like 99.95. That is the percent of the time the link is up and operational. To give you an idea what 5 nines are, right? The farthest column out, that is 5 minutes of outage time per year in aggregate. That means if you add up all the outages together, you're at 5 minutes. Let's get a little more specific. So I'm going to show you this. Okay, this is with a 1-foot dish. Let's add a 2-foot dish. And this is what changed, is that 2-foot dish, as you see, there's now a little bit more energy that can be applied to the unit, and therefore your availability will go up. So as you go up farther out, like if this link was 10 miles, you'd still get 10 gigs, but at a lower availability, okay? This gets it specifically, this is actually all from our link budget calculator. So this actually shows you the output at 1 mile. So what we're going to see here is that with a at 5 nines, it is 5 minutes and 15 seconds of potential downtime. With even at 99%, you're talking about at 99.9%, you're at 8 hours of potential downtime. But let's really look at this closely. That means it really depends on how much rain you get. So to drop it off a full rate, and this at 1 mile, and I picked the middle of the country, Lincoln, Nebraska, is it would take a rainfall of 0.79 inches or almost an inch of rain per hour to take it off a full rate. It would take literally a rainstorm of 4.92 inches an hour, that's flood stage, to actually drop the link. Okay, so just take it off of its full rate is almost an inch to actually drop the link. It's at 3.92. You're actually worried more about whether your house is going to float down the road at that point. So this is all based on our link budget calculator. So our link budget calculator is the tool that we use to actually calculate out the link. Okay, it specifically will give you the operating parameters of the link, and because interference doesn't really exist in millimeter wave, specifically on the point-to-point links, is that we guarantee those results. Whatever you get off the link budget calculator is what you will see on your real link. You'll get that or better. So keep that in mind. It's really it is something that you can really take to your client and say, here's what the links can perform. We can guarantee this because the manufacturer guarantees this. And we can do, and it's us and all of our competitors all do the same thing. We all run off the same science and the same statistics. In terms of interference, and you're probably going to say, well, don't you get interference? Just to give you an example, on a single point, you can run, let's just take, we'll take the E-band, and on a single point, we've got 8 non-overlapping channels. We have 2 polarities to work with. And then on top of that, this is our standard 1 gig full duplex link. And on top of that, to reuse all those 8 channels and polarities, you only have to move the antenna 6 degrees. And you can reuse all those frequencies and polarities again. That means if you do the math really quickly, 60 positions, 8 channels with 2 polarities, you can put almost 900 radios theoretically on a single point. In my nearly 4 years with SFU, I've yet to see a true case of interference. And to give you a realistic example, you take the building called One Wilshire in LA. It's one of the most, if not the most important internet networking site in North America. That particular facility has well over 100 millimeter wave radios, half of which are SFUs. And all those radios operate with 0 interference on an active rooftop. So let's get really into deployments here. So what really is important when you go to install, and really that's at the crux of what this whole talk's about. First off, millimeter wave is line of sight, but the reality is, to get above 100 Mbps, and that's really what everyone talks about nowadays, is getting into 100 Mbps or a gig. To get that kind of throughput, you have to have line of sight. There is no line of sight technology that exists that can go non-line of sight at a gig, or even above 100 megs at any distance. That's the reality of wireless data. You can go short ranges through walls in your house, maybe a few walls in a building, but that's it. You're not going to go any true distance that's really above 50 meters with any technology without line of sight. Okay, there's lots of technologies out there that say, oh, we can do 500 megs, or we can do 800 megs, or we can do a gig. And we also do line of sight, but you say, well, what can you do in non-line of sight? Non-line of sight, oh, well, it's 50 megs. Oh, it's 25 megs. Well, we can do non-line of sight. Big difference between line of sight capability and non-line of sight capability, okay? So the key thing is you always want to plan your paths with clear line of sight. Now, the beautiful thing is that you don't need a huge Fresnel zone. That's a beautiful thing. The Fresnel zone on millimeter wave is roughly less than 1/3 the size of, let's say, a 5/8 link. So therefore, just to give you a quick example, on let's say a standard 1/3 of a mile link, on 5/8, you're talking about a Fresnel of about 7.5 feet. Whereas on, whereas millimeter wave is 2.5 feet. So much, much smaller than roughly 1/3 the size. So it's a much smaller distance, and it's a much more robust technology in terms of signal stability and potential interference, especially when you start talking distances. Now, if you start going out like miles, you have to start worrying about antenna height with 5/8, where again, with millimeter wave, if you're talking about a 2-mile link, you're still only talking a Fresnel of 15 feet. That means above ground interference, meaning trucks and bushes and shrubs, you only have to, you have that plus 15 feet is all you have to be off the ground, which is really small. The same link with 5/8, you're talking, you'd be at 2 miles, you'd be almost 80 feet above the ground. Okay. The other thing is The key thing though is finding a stable mounting source. And the larger antennas require a more stable source. And keep in mind, millimeter wave, you're aligning something that's only 7 millimeters. The beam itself is only 7 millimeters. So it's very precise. It's like aligning two antennas, two lasers. So the key thing is you need to make sure your source is relatively stable. Now, our 6-inch dishes are designed to allow a little bit of movement. So you can mount it on street lights. You can mount it on intersections. Our multi-point stuff, that can actually track moving objects, and that's a whole different set of rules, and we'll talk about that in a minute. But on the point-to-points, you have to have a stable source. The torsional forces, which is the moving force for our 6-inch dish, is 1.25 degrees. For our 1-foot dish, it's 0.5 degrees. For a 2-foot dish, it's 0.25 degrees. So that means that you have to be very, very stable on the mounting source. And the bigger the dish, the more stable the source. Like a 2-foot dish, it needs to be rock solid. You need to be having it on a thick wall, 2.5-inch pole that's not very high, that's very stable with no moving force at all. Whereas with our 6-inch dish, you could have it on an intersection which sways a little bit, okay? The other key thing is grounding. This is probably the largest issue we have with installation is improperly grounded units. The one thing to remember is you have to have a true earth ground. If you're grounding it to the pole you're mounting it to, make sure that that structure is grounded. In fact, what you probably want to do is put a grounding point directly from whatever your grounding source is to a central grounding point on your mounting structure, and then attach your ground wires to the antenna. Grounding's key. And it's not necessarily that you're trying to protect it from lightning. The reality is if lightning hits our radios or anybody else's, they're gone. What you're trying to do with grounding is actually part of the electrical system of the unit. And you're going to significantly increase longevity of the unit if you properly ground with ground. And you also need shielded cable, that's shielded Cat 5 or Cat 6, with shielded connectors. And just to give you an idea of what our mean time to failure on our units is that our units vary from about 80 years mean time to failure to we have units go 90 years mean time to failure. And we have a statistical average on most of our radios of 105 years mean time to failure. So these radios will last, but it has to be installed properly in order to get those kind of statistics. You need to install properly. Cannot stress that enough. So just review, make sure you have a true earth ground. If you're on a rooftop, you can usually contact building management and they can show you exactly, it's in most states, it's code where the grounding point is. And if you're doing it, the traditional spec is, it's a 4-foot rod pounded into the ground that you attach to. So that's the classic example of true earth ground. The other key thing with our radios is get training, please. That's, if you haven't been through SFU training, we don't charge for it. Our stuff is actually pretty useful. We try to make it so, again, we're not trying to, indoctrinate you in why SFU is so much better than everybody else. We think we're pretty good, but we want to make sure that you know about the technology itself, because millimeter wave is the future. It is 5G. It's what's coming. And the more you know about it, the better you're going to be. So please go through e-learning. We don't charge for it. We really encourage any of our partners to go through it. It is something that you really will benefit from. Then after you go through e-learning, contact myself or any one of my colleagues into the professional services group, and we'll go through, spend 30 minutes on a webinar, go through and answer any questions you have from e-learning, and they would go through some of the finer points of installation, because really the critical thing in millimeter wave and point-to-points is alignment. Alignment, because all those other issues that exist in RF simply don't exist in millimeter wave. What is a bear is working through alignment. And once you get to know alignment, and just to give you an idea how long alignment will take, is that first time you do a millimeter wave link, it's going to be about 4 hours. You want to plan a break. Make sure you schedule plenty of time the first time you do it, and that's with training. The second time you do it, it'll take 1 to 3 hours. The third time you do it, it'll be under 30 minutes. In fact, you'll spend more time doing lockdown of the radio than you will on doing alignment. You'll get that fast. But it's just a process. It's like learning how to ride a bicycle. Once you get it, you understand it, you'll move forward and it'll be great, okay? Another thing that you want to remember is know the distance of the link that you're doing. And one of my pet peeves when people call and they say, like I had literally a call last night where I was working with a crew and I said, how long's your link? And they said, oh, about 2 miles. When I went on Google Earth and looked at the points, it was 1.45 miles, okay? You got to know the distances, and you want to be, when it's shorter, the distance becomes more critical. So at shorter distances, like under a mile, you want to know within about 10, 15, 20 feet of your accurate distance. When it's over a mile, you want to be within 20, 40, 50 feet of the actual distance. But knowing the accurate distance is really important. It affects what we call the RSSI, or Received Signal Strength Indication. This is what you align to. You need to be within 4 dB of being aligned in order to call yourself aligned, and this is critical. In fact, when you're going through and charting out, you want to document, and this is what we cover in our installation training, is you want to document out your links. You want to put in what your calculated RSSI and what your actual RSSI is. Documenting what you do in the field is key. By doing that, you're serving your client and your system better. You are giving yourself, to know what you did. And if there's a problem ever down the road, you can go see, oh, my RSSI that we achieved was a neg 36. We're now seeing a neg 42. Somebody must have come and knocked the link, or there's a problem with the link, one of the two. And it really helps with troubleshooting. And also keep in mind, there's other things, is that when you do the alignment, you need to be within 4 dB of the line. Now, if it's below 35, keep in mind saturation on a millimeter wave link, and this is pretty true for most manufacturers, is a neg 35 dBm. But you'll get in situations on shorter links where you're aligning down to a neg 20, neg 25, neg 27. You still align to that point where you're at a neg 27. And then what you do is you turn down the power, because you want to make sure the 2 units are aligned like 2 lasers pointing at each other. And then you turn the power so your unit goes up to a neg 35 power output. Okay, and these are things we cover in our installation training. I don't want to dive too much into it. I'm trying to keep this more 40,000 foot level. Okay.
So Tim, we have a question on grounding
Sure.
from Dennis. The question was regarding grounding. Are Cat 5, Cat 6 cable ground kits also required?
It's not ground kits. What we want is we want a shielded cable with a shielded connector. You don't need a Cat 5 ground kit. It's a really good question. It's just you want to be using a shielded cable with shielded connectors. That's what we really look for. In fact, that's what the industry is going to. If you actually look at pretty much in the radio industry, we're almost all either required or we call it a best practice with using shielded cables with shielded connectors. Even in the security camera industry, several of the top manufacturers have moved to where they're calling it best practices to using a shielded cable with a shielded connector. Okay, good question. Here's how you do the long range links. Okay, we call this an overbuild, and in our software we also refer to it as NNM, extended M. So what this does is within the radio you can attach a secondary radio. It could be a 11 gigahertz links. That's commonly what we use. But in rural areas, you could still get away with using a 5/8 link. But literally what it does is this is when you start going above 2, 2.5, or 3 miles, when you start pushing out to 5 and 10 miles, which millimeter wave here can't really do. Now keep in mind, millimeter wave when it's in space can go tens of thousands of miles. In fact, just to give you a really short history of millimeter wave, is that it was discovered back in the 1890s. They tried making it work in World War II, but they found that it wouldn't work in analog. And that's one of the key differentiators of millimeter wave. It doesn't work in analog. And then they tried making it work again in the 1960s, but they realized then they didn't have the computational power. So in the 1980s, DARPA took this on as part of the Star Wars project. And this is how our satellites today communicate between each other, is with millimeter wave. And because when you are in the vacuum of space, millimeter wave, which doesn't beam spread, it will go, for a very long ways. When you start talking about Earth, now you have atmosphere and you have rain to deal with. So therefore, that's your limiting factors. So what this does is use a secondary link that doesn't have necessarily as high as carrying capacity. Let's say 11 gigahertz link at 10 miles will go somewhere between 3 to 400 Mbps half duplex. So you can actually plug one of those radios into our radio directly. And then literally you have from our radio, you have, our radio will actually sense, and it'll be there, it'll be operating. And then when it reaches the point where it says, okay, because it's a long distance, I've now dropped to the point where I've reached my lowest modulation level and its link's going to drop. Actually, and by the way, you determine at which point, at which modulation you want to set it for. This is an internal setting where you can set it for whatever modulation you decide. It'll kick over to that secondary link. Secondary link backs it up and it goes over. It's very fast. It happens at 50 milliseconds, so it's hitless. It goes over to the secondary link, and then when it's ready to pull it back, our unit just kicks it right back. There's no extra equipment to buy. It's just built into the unit. The only thing it is just a license feature, and it's one of our more affordable licenses.
So Tim, we had a follow-up question on grounding. There's a situation where they're going to be deploying, using solar, wind, or other alternative power sources. And so the question was, do we need to install a true earth ground rod at each location?
If there is not a grounding source defined by the building, if it's a source that's, if you're just out, like if it's a solar application, absolutely. You want to add, in fact, it's not just our equipment that will want that, is that your solar equipment and your power equipment will want that same ground. And it'll benefit all your equipment at site. Okay, good question again, good follow-up. This is a 9-mile link. In fact, they have a 9-mile and a 10-mile link here. They actually have a second link on the site. They're using 11 gigahertz to back it up. This was actually done over in the LA area. This was actually done during monsoon, the rainy season in the fall. This was this was 2 falls ago when we actually monitored this link every day. They only had 5 drops during the 2 months of operation that we were monitoring. These were all short, and this is an incredibly long link. The actual uptime was over 99.6% uptime, which is common. So that means really what we're building for is we're trying to really fill in that loss of 0.4% downtime. And that's really what we're looking at. And the link still, most of the time, is operating at full capacity. And the one thing that they really notice is between when it's running on the millimeter wave link versus the 11 gigahertz link, is when they're on millimeter wave, the latency is much lower. The latency and that's one of the key characteristics of millimeter wave, it's highly low latency. On our 2 gig links, it's 80, not milliseconds, but 80 microseconds of latency. So even though when they kick over to the 11 gigahertz link, it's still good. They're at about 6 milliseconds. But the one thing that the network operators notice is they can really tell in latency what changes when they go from a millimeter wave link to the 11 gigahertz link. So let's kind of go over some of really what we're talking about is really the key thing here is how do you really deploy millimeter wave network? What's the best use case? Well, really, it's a blend of fiber and millimeter wave, because millimeter wave is very close in operation, and in the way the network looks at it, it's like fiber, okay? And some people call it virtual fiber. So the key thing is that you blend where fiber works the best, use fiber. In some cases, it's existing in the ground, it's already there, you can pop straight into it. But in other cases, it's more efficient because some fiber routes go in these very in non-direct routes, whereas with millimeter wave you can go through direct routes. And in fact, there's a specific case, I'll kind of go into where we talk about WebPass, and well, we'll get to that slide and I'll touch about them. So this is so here's our lineup and here's how we do. And this is really the only SFU product we're going to talk about. Essentially what we do is we've got our multi-point starting at the bottom here. We've got our multi-point units, and that's really for the last, 1,000, 1,100 feet. That's what you're going to go to the house itself, to the neighborhood. And that seems kind of short, but I just finished doing a neighborhood last night of 350 homes, and gee whiz, distance is not the issue. It's trying to get enough units packed in the area to cover that many homes. It works on a 1:8 ratio. So you have one radio to 8 client devices, okay? Then you need to connect those. You can use various of our different radios, like you can use our 1200 TX to 1200 FX, that's our 1 gig radios. We've got our 500 megahertz radios. We've got which are the 60 gigahertz, which are the EH500 600s. They do 1 gig half duplex, the 600 does, and the 500 is just a more cost-effective alternative, essentially for cameras and whatnot. Then you go to an aggregation radio, and that's like our bigger radios. That's our 8010, our new 10 gig full duplex. And by the way, when we say a gig, we really talk, it's a gig. It's not like an air interface rate, whereas like on Wi-Fi where they say, oh yeah, we can do 1.2 gigs. But when have you seen a Wi-Fi connection at distance go beyond 200 megs or 250 megs? It just, even when you're right next to the radio, you won't get higher than 250. When we say gig, it's truly a gig. So therefore, let's say if you look at our 1 gig full duplex radio, when you actually measure it, it'll be about 940 Mbps, and you're losing about 60 Mbps due to TCP packet header loss, which is the exact same as if you're running it through a switch on fiber. No difference. So it's essentially, they're fully equivalent. Then you move to our core backbone radios, which is our 8010 and 5500. 8010, the 10 gig full duplex, it's new, it's an amazing radio. The 5500, that's our layer 1 radio. That one has a latency of 5 microseconds. It's stupid fast, and it is as clean as connection as you're going to find. And then our transport, in other words, to do long haul, the 2 radios you would do that with is an 8010 or the 2500. 2500 is designed to do distances. That's our longest distance radio. 8010 can almost do what the 2500 is, but the 2500 is really specialized into doing long distance links. The longest link I think we've got in operation on that is about 13 or 14 miles, right around in there. But that's the SFU lineup of SFU devices. And there's also this new little guy right here. I noticed they updated the slide. This one is our new compact TU on our multi-point, about the size of your cell phone, if you give you an idea of the size of that device. Other sort of offerings that we can assist you with is we have SFU Smart Haul service as a software as a service applications. So we've got the Wireless Network Design Engine, or WINDY, which is a network design tool. We have our link budget calculator. That's how you look at exactly what the link is, and that's what we just went through a little bit earlier. And we do have a financial analysis calculator that your accountants will love. And then we also have our newest Smart Haul EMS, an element management system. It's different than an NMS. We're not trying to manage other people's devices with this system. We're just trying to manage our devices. So when an EMS, how it's different than an NMS, NMS is a network management system, whereas the EMS is an element management system. So it manages our devices rather than trying to manage the whole network. And it's specific to our devices. And it's a really nice system. So if you're running the kind of operation where you just want to see your devices, the specific part of the network we're operating in, EMS is a perfect solution. However, we're fully compatible with most NMSs. We fully support SMP v2 and v3. Okay, a couple of
we had a question about higher bands. What are the plans, or what's going on in the 92 gigahertz, 128 gigahertz arenas?
Right now, there are some firms with some devices in there. it really, the higher you go, it means that you now have more limitations. And right now, we're so far from saturation on the 7080. 90 is kind of cool. 120 is kind of cool, but there's just not a lot of motivation to go there. The higher frequency you go, you're just going to shorten your distances. You're going to increase your the availability, or the availabilities are going to get shorter. So that's the problem with, it's a trade-off. And if you push to the 90 gigahertz or 120, it's interesting, but right now it's and there's a couple firms doing it, but it's just not, there's not a real demand for it, and it's really not where the industry's going right now. But it's fun to look at.
So if I could add to that, we at SFU, we are involved in a number of the standards bodies around the world that are developing these technologies. So we are contributing from an R&D perspective into standards. But as Tim noted, it's not on our roadmap for the next 12 months, certainly. And we're really waiting and watching the market. The other challenge that we have with those higher frequency bands is there's no ecosystem of components. So building products at those frequencies today is very, very expensive. Will we get there? Probably, but not today and not within the next year.
Okay, thanks a lot. Thanks for that, David. So, and David's a person you should know. He's actually runs product management, so he knows his stuff. So here's a couple of operations. This was Jade Communications. They were an outfit out of Colorado. They had a fire that ran through the town that they operated in. They were able to, in a matter of days, start bringing up and replacing existing network communications, because literally the fire wiped out everything was on poles, and it completely wiped out most of the infrastructure. They were able to bring it up within days, and they brought back up the network, and they are continuing to deploy with our stuff. It's a really amazing use case. It was superb, especially considering what we've seen happening as of late. C-Spire. C-Spire is a local exchange carrier in the southeastern U.S., and they're using our EH600s to connect up rooftops, and from there they're propagating out, and they're by doing that, they're actually now, rather than putting a lot of fiber, they're using our mmWave units. A very stable and reliable system. Right now, they've got up and operational. I think it's somewhere right around 1,000 homes. It's really a great concept. We've actually done this concept we've been doing this concept as long as 3 years ago. So we've been doing this for quite a while. It's a very proven system. This is one of our most interesting. This is the city of San Francisco. This has more fiber per square meter than any other place on the planet. And right there, all those green dots you see, those are all millimeter wavelengths, and they all operate with no interference. And by the way, that's just SFU millimeter wavelengths in downtown San Francisco. And we work across the spectrum. We work with video surveillance systems. We work with bus systems. Hospitals use us. There's a lot of ISPs that use us in that area. Several of the largest ones. One of the big ones is called WebPass. WebPass is kind of interesting. In markets where they and Google competed with each other, they consistently beat Google statistically. Even though Google literally maxed out their fiber network and did everything they could to it, they kept being beat by WebPass. Why? Because WebPass ran both fiber and millimeter wave, and they kind of did where millimeter waves made sense. They could do more direct routing, and they could create a more efficient network. So what ended up happening about a year and a half, 2 years ago, is Google bought WebPass. So in fact, there was a nice little quote from the founder of WebPass about our equipment. It was really nice. Vail, Colorado. The issue here is they had a Wi-Fi system that they were trying to run cameras off of, and they were trying to run Wi-Fi. Neither of them worked very well. The camera system would come in and out. What we did is, rather than scrapping the Wi-Fi stuff, we just recast it and had the Wi-Fi go 2458 at the as for client access, and then we backhaul the camera and the Wi-Fi through our 60 gigahertz units. They went from the video working only some of the time to the video working perfectly, and their Wi-Fi went from about 2 or 3 megs potential of service to 100 megs customer service. That means public Wi-Fi on 100 megs, and it's been operating for over 2 years. I've actually been to Vail and actually seen someone smile when they've used their phones. And they've done 3 or 4 network upgrades to that, where they've just expanded the system. In fact, right after we built the system, they actually had a fiber. They had somebody digging in their city, and they yanked up some of their fiber. So they called us up and they said, "Can we use your system to back up our existing network infrastructure?" And we said, "Yeah, but we don't know. It wasn't designed for that." But they did. It worked for 3 weeks while they repaired the fiber, and it worked out pretty well. John Glenn International Airport. This one was a test with the airport and the FAA. They wanted to make sure that millimeter wave wasn't affected by traffic. This particular link was going across their active main runway. It was planned so it would be near, so the planes would fly near it, but not through it. But it went directly over the runway. The planes usually were wheels up beyond where the link was. And then we had another multi-haul link, which actually drove through in an active taxiway. Those were 2 things we're testing for. After the test was finished, they liked the link so well, they said, "Can we just buy it and leave it in place?" And we said, "It's used." And they said, "We don't care, it works." So, and it's still in process. It's there today. This is City of Wichita, Kansas. This was one of our first significant deployments with multi-haul or multi-point units. These have a 90-degree area of coverage, and it's a scanning antenna. In fact, this was the first scanning antenna that literally was for the outdoor space above 12 gigahertz. It was something that nobody knew could work, and we made it work. And now there's a few other people doing it too, but this was the very first, and it's pretty cool. It'll actually track moving objects when you put it up. Unlike our point-to-points, which are have to have on a very stable pole, and you have to be very precise in alignment. With the multi-point, you just put it up and it works. It's really nice for short deployments, quick deployments. It works really nicely. We see this used in temporary venues, and in this case, this is supporting a downtown camera system. They've actually done 4, since the system was installed, they've done 4 expansions of this system, and it's worked out really well. King City, California. This is a city that had a higher murder rate in real terms than the city of Oakland. Literally, when the system was under construction, they just had up and on and were testing it. They actually caught a murder in progress with the camera system, even though the system wasn't fully up yet. But it was evidence, and they actually caught the person who did it. But this is a system was built out, and the city's crime rate has dropped dramatically. It's been pretty impressive. Port of Long Beach. This is one of the largest ports in North America. This about 2 years ago, they switched over and standardized on a single radio format. They standard on ours. This is in a very robust operational environment. In fact, their sister port, Port of LA, is also converting over to SFU. That means between the Port of LA and the Port of Long Beach, that makes it the largest port complex in the Western Hemisphere that is now all SFU. And it's really a beautiful system. They use fiber and millimeter wave, and the 2 run seamlessly together. In fact, they actually had an outage that they didn't even notice for several days, because it just automatically kicked over from the fiber over to their millimeter wave unit. In fact, it was an error in their monitoring system that they found out that was the cause of the issue. So really, to kind of go through it, just what we've covered is that it's really a robust technology. We go up to 10 gigs full duplex, and that's true 10 gigs full duplex. It's just like it was a piece of fiber. It is incredibly secure. We didn't really hit on security that much in this presentation, but when we do our trainings, we can go through and we can show you how secure it is. It's literally one of the most, if not the most secure transmission technology out there. And not just talking about radios easily, but I'm comparing it to copper, which we're way more secure than copper. And we're just as secure, if not more secure than fiber. It is really, this is the future. This is when people talk about 5G, this is what the system is. And when you properly install it and you get it set up, these systems will work, and they'll work just like if it was fiber. In fact, there was a system I was working on where they were saying, well, our fiber stuff, we plan on a mean time to failure of 30 years. And I said, well, your wireless will be 80 or 90 years, depending on the devices. And they went, longer than fiber? And realistically, this stuff is functionally, in many cases, better than fiber. I'm not saying you should replace fiber. I'm saying it's a medium that works seamlessly with fiber. And really, hybrid fiber wireless networks is really where the future lies. And the thing that interference doesn't exist, and literally, I've yet, in my 4 years at Ciclo, I've yet to see a true case of interference. The only time I've ever seen interference is when an installer went and did a daisy chain in a row, and they were all in line, of 4 radios all in the same channel. You actually have to try to create interference. And it's really, realistically, you just don't see interference. It just doesn't happen. And it really works. You know, we've got operational systems from on the North Slope, Alaska, which is very cold and very harsh, to high rain, wet environments like, you know, the bayous of the Mississippi and Louisiana. It is just we work in a whole range of environments, in the desert, in the heat, and it's very stable and very reliable. And the thing is, we have the tools that you can use to help you design systems. So it's really a really good tool in your toolbox. Shouldn't be your only tool, but it's a really solid tool that you can use to deploy networks. And that's pretty much all I've got. Questions, anyone?
So I have another question for you, Tim. When do you decide to use the V-band or E-band in a point-to-point deployment? What factors should you be considering? Well,
it's really, you want to look at capacity, how much throughput you need. If you need over a gig, you really need to be looking at E-band. Because right now you can do up to a gig on 60 gigahertz. And keep in mind, it is unlicensed, which is still, there's so much spectrum there, you just don't see interference. But you really, you know, on point-to-point links, typically anything over really a mile. So if I'm looking at distance or anything over a gig, you definitely want to be looking at V-band, really on E-band, on the point-to-point links. It's sort of like, think of it in terms of this way: you've got your existing connections on let's say V-band, which are like your, let's say, under the treetops. It's like your local connections. And when you're trying to put in your longer haul links, you know, of whether it's a half mile, mile, or 2 miles, or even further out, then you want to go to E-band. That's really where you're going to get your, you know, your higher capacities and longer distances. And we can push those out solidly with the radio alone. We have links going out in most areas out to 2.5, 2.8 miles.
Okay, we have another question regarding DFS and other military or other agencies using these frequencies. So in the 5 gigahertz band, there is the DFS band where you have to be aware and be able to detect radar, and if you detect it, you have to move on. So the question is, what happens with millimeter wave?
There's no DFS.
Or other agencies.
There's no DFS. There's no interference. We don't have to worry about it. It doesn't exist. DFS was yeah, it doesn't exist.
Are there other agencies using these frequencies that they have to worry about?
No. And if the military does use some of these frequencies, they operate under the same rules you all operate under. And there's not, again, all those, multipath doesn't exist in the millimeter wave. All those other DFS that's how you got the 5.4 band, was that the industry made a trade that FCC gave 5.4 as long as they did DFS in the lower frequencies, the 5.3, you went to DFS, That was the trade-off that you made with DFS. It doesn't exist in millimeter wave. All those trade-offs and and trying to get that little bit of extra energy, again, doesn't exist in millimeter wave at all. So no DFS. Nothing to worry about like that.
So no DFS, and I think more importantly, there's, I think part of the reason with the 5 gig was that the Wi-Fi was in some cases a secondary use. So it had to bow out for the primary use. And in the millimeter waves, the 60, 70, 80, that does not exist. So there's no primary use and secondary use in those bands. If you're in the 60 gig, everybody's equal. If you're in the 70, 80, everybody has to license.
No.
I think that, okay. I think that is all the questions we have here today. So we're going to go ahead and wrap up this webinar. Wanted to thank everybody for your attendance. We are always open to feedback and constructive comments as to how we can do better. Hopefully this webinar was able to give you a little bit of insight on how millimeter wave is somewhat fundamentally different than what you're used to if you're doing 5 gigahertz today. With that, we're going to close the webinar. And again, thank you all for coming.
Thanks.